Thank you for joining us for this informative American Institute of Chemical Engineers webinar sponsored by Provenance Consulting, when the only things consistent about your PHAs are inconsistencies. Our speaker is Patrick Fisher. Patrick Fisher is a chemical engineer with experience in the industrial and refining industries with proven results in process hazard analysis, layer of protection analysis facilitation, and training and safety instrumented function design. As a PHA facilitator, he helps large organizations meet the PHA, MOC, PSSR, and PSI requirements of the OSHA PSM standard. His background includes publications on risk analysis, minimizing independent protection layers, and leading indicators of process safety. One quick note before I turn the session over to Patrick Fisher. As described more fully on this slide, the American Institute of Chemical Engineers assumes no legal liability or responsibility for the use or misuse of the content in this webinar. And now I'd like to welcome Patrick Fisher. Hello, Patrick.
Hello. Thank you, Pam, for that wonderful introduction. And thank you to all of our attendees for joining us today. As introduced, my name is Patrick Fisher. I'm a process engineer with a background in process safety and specifically PHAs and LOPAs. I work with Provenance Consulting, who specialize in understanding and assisting with the process safety needs of our clients. Today I'm going to be talking about consistency in process hazard analysis, or PHAs. It's something that I've seen becoming a larger and larger concern over the past few years, particularly at the really large organizations. If you're listening to this, you probably have similar concerns within your company or organization. I want to start out by saying you're definitely not alone. I've yet to find a company that has really gotten consistency down pat when it comes to PHAs. Really, I'm not even sure it's 100% possible. What I'm going to be showing you today are not necessarily magic bullets, but really a selection of issues that come up around inconsistencies and a few ways that some industry players are currently addressing PHA consistency. Now, to start this out, I believe that every good presentation should start with a quote that really sets the mood. So for today, I set out to find something that really captured why consistency is important in our lives. Well, it turns out that it's rather hard to find any good quotes about consistency. It looks like most people that come up with quotes are philosophers and artists, and they don't tend to like the same thing happening every day. And when I saw some rather scathing quotes from people like Oscar Wilde, I thought about it a little bit more and wondered to myself, why do we actually strive for consistency? Should we really be doing that? And the more I thought about it, the more I thought about the purpose of PHAs. And I came to the conclusion that no, we don't want perfect consistency in our PHAs. PHAs and LOPAs are ultimately brainstorming activities, and the day where we start having perfectly consistent PHAs is going to be the day where we stop finding new concerns. And that's the last thing we want. So I thought even more about it, and I realized that when I talk about consistency and when PSM groups talk about consistency, they mean something a little bit different than perhaps Mr. Wilde or Mr. Berenson mean. What I mean is a conformity in logic and having the same information and coming to the same conclusions even if the path is slightly different. And that's really what we all strive for. We don't want everything to be the exact same when we do a PHA. We just want the results to be, at the very least, similar. So we're going to be talking about three major topics today. The first is going to be about the impact of inconsistencies on cost and non-cost impacts. We're also going to talk about why the inconsistencies occur and how the inconsistencies can be avoided, or at least ways that industry is currently looking at avoiding inconsistencies. So throughout this presentation, I'm going to be talking about RT Industries. They are a fictional and perhaps highly exaggerated organization that I've created to try to represent the issues that most of industry is seeing today. RT is a company that's just trying to do the right thing under the PSM regulations. So far, they've been following the letter of the law, and they have had a few incidents over the years and sometimes get some fines, but those always seem to happen. However, recently, one of their competitors, who makes a chemical very similar to what RT makes, had an incident, and the VP of operations told the PSM manager, it's time to review our process safety and make sure that such an incident could not happen in any of their facilities. So they looked into it and they found that there were 3 different facilities, all which produced the same chemical. Each of these facilities went through a HAZOP process and came out with completely different results. Even though their design was almost identical and the scenarios they looked at were almost identical, in the end, the recommendations that came out of it were completely different. So we're going to look at how that actually happened, why it happened, and what RT eventually did to try to make things better. So to start out with the impact. Why was this an issue? First, we're going to walk through a HAZOP and LOPA at RT to demonstrate the types of inconsistencies you might see and the way that they build up. We're also going to look at how this impacted the cost at RT and what the non-cost impacts were. So to start out and expand a little bit more on what RT is, they are sort of your middle-of-the-road, average organization when it comes to PSM. There's nothing exceptional about them. They're nothing extremely bad or extremely good. They have a fairly standard risk matrix and a fairly standard PHA and LOPA process. So when they were tasked to do this, the 3 PHAs across 3 different facilities, they all had the same information to start with and the same types of equipment. So they were looking at a centrifugal pump that's pumping a gasoline-like substance. Downstream, there is a discharge valve, and previous PHAs at each of the 3 organizations had identified the need for 2 safeguards, a high-pressure alarm, and a local hazardous atmosphere detector. Each of the 3 teams looked at this node and tried to come up with a consequence if the discharge valve went closed. HAZOP Team 1 had recently had a very similar experience and saw a seal leak that resulted in a fire. So they came up with the consequence that the pump's going to deadhead, seal gets damaged, and gasoline spill immediately ignites due to the hot seal. In their case, they didn't have a person injured, but they realized that someone, if they had been nearby, could have been pretty severely burnt. So they said that could be a permanent disability. HAZOP Team 2, however, has not had a recent event, but had heard about what happened at Facility 1. So they came up with approximately the same consequence, deadheading and permanent disability. PHA Team 3, however, had not seen that particular incident and recently had been having a lot of seal leaks, and nothing ever seemed to really come of those seal leaks. So they agreed in general with the series of events, but said that it would be a small fire resulting in a first aid injury. So already here we see a slight difference based on the experience. We have 2 different consequences depending on the team. Now, I've seen times where procedures call for the PHA facilitator to step in and adjust this to the more realistic consequence is. However, in reality, both of these consequences are realistic based on what they've seen in their facilities. So the PHA facilitator depends on the team's experience, training, and judgment to come up with these consequences. And it's not their place to say one is correct or one is not, unless they have particular information that can guide that. So all 3 teams are doing what's required to be done based on the procedures and the OSHA PSM requirements. Next, each of the 3 teams needs to come up with safeguards. Team 1, having recently experienced this, knew that there was a high discharge pressure alarm and the hazardous atmosphere detector went off, and that's what ultimately prevented someone from being hurt. So they think that there's 2 safeguards there. Team 2, however, saw that the seal leak had happened anyways and realized that the high discharge pressure alarm may not have come in, and the hazardous atmosphere detector doesn't really help if someone's there. So they said, no safeguards available. Team 3, given that they were only looking at a potential first aid injury, figured a high discharge pressure alarm would be enough and listed that as a safeguard. Once again, all 3 teams are doing something that is acceptable. They're basing their safeguards on their experience about what's going to work. However, all 3 are completely different here. The next step is going to be to risk rank this for each of the 3 teams. And to do so, we need a likelihood. We already have the severity. Most organizations seen at this point look at the likelihood of the initial valve failure and then drop the likelihood by a level depending on the safeguards. So for Team 1, they have 2 safeguards. They drop from a likelihood of likely to remote. Team 2, having no safeguards, keeps a likelihood, and Team 3 with 1 safeguard is right in the middle in the unlikely. So what does this look like when it comes to the risk matrix? Well, Team 1 said that they'd have a permanent disability that was remote, and they get a medium risk. Team 2, on the other hand, had the same permanent disability, but a likely scenario because they didn't have any safeguards. Team 3, given that they didn't think the severity was very high, have a first aid and a low risk overall based on the unlikely likelihood. So what we see here is we have 3 teams that, going through their own experience and the information that they have, came up with 3 drastically different risk rankings. And this is not particularly unusual to see in a PHA if you present different groups with the same information. It really is going to depend on the assumptions that you make and the experience of the team. What's perhaps worse than this is the next step. At RT, they go to LOPA if the severity is a 4 or a 5. So what we have is 2 of the teams going on to additional, more rigorous analysis, and 1 of the teams is not. So when it comes to recommendations out of the HAZOP, we have Team 1 at a medium acceptable risk ranking. Doesn't need any recommendation, but needs to review in the LOPA. Team 2, having an unacceptable risk ranking, needs to do something like add a high discharge pressure or trip on the pump, and they're also going to review this scenario in LOPA. Team 3, on the other hand, has a completely acceptable risk ranking, and being a first aid, they don't need to do LOPA. So we're already seeing difference in the recommendations that are coming out of this. So what does this actually look like within the facility? Team 1 has a pretty similar setup to what they started with, a hazardous atmosphere detector and a high discharge pressure alarm. Team 2, however, has added in a trip and removed the other 2 safeguards because they're not needed. And Team 3 is sticking with just a high discharge pressure alarm. So we have differences in the design creeping up based on the HAZOP result. On top of that, the first 2 teams are going to go to LOPA, and the 3rd team is not. So what does that mean when we actually get to the LOPA? Team 1 came up with a permanent disability, and based on RT's requirements, they need 2 IPLs. Also based on the requirements, they can take the high pressure alarm as 1 level. Given that they're still missing 1, they're going to make a recommendation to add a still 1 high discharge pressure trip. LOPA Team 2 also requires 2 IPLs, doesn't have any, and therefore their recommendation here is to add a still 2 high discharge pressure trip. Team 3 never even got to the LOPA stage, so they're not going to have any type of SIL or LOPA recommendation in that case because they don't need it based on a first aid injury. So what does this look like after the LOPA's over? Team 1 has a still 1 and a high pressure alarm. Team 2 has a 2 out of 3 transmitter still 2 system with no high discharge pressure alarm. And Team 3 has only a high pressure alarm. All of this creeped up from compounding inconsistencies all of which were reasonable on their own. However, at this point, we have pretty large impacts. There's certain cost impacts that we'll go over, but there's also operability impacts. What happens when you're trying to cross-train your operations staff at the different facilities and they're looking at completely different safeguarding? What this can lead to is issues with bypassing equipment or not trusting equipment or not thinking that equipment is required. So if someone is trained in Facility 3 and moves to Facility 2, they're going to see a SIL 2 trip and think it's completely out to lunch. And it can be really hard to tell which is actually correct. Let's look at the cost impact, though. Every IPL has a certain cost to install and then to maintain. These costs really build up over time, and what you'll see is the three different teams, given their different IPLs, have order of magnitude different costs. Now, these are just examples, but you see this type of range depending on the facilities and the experience of the PHA team when they're coming up with safeguards that are required. More importantly than this, possibly, is that if RT later decides that one of these is correct, they have to rip out two of them and spend a bunch of money to get it right. Now, what happens if there's an incident? All of a sudden, we're going to need to look back at our PHAs. In particular, perhaps if someone was injured, OSHA might show up, and now we're in trouble. They're going to ask to see, at the very least, the PHA of the facility where the event happened. It's possible they'll ask for similar PHAs at different facilities. So what they're going to see is three teams that risk ranked this completely differently. And perhaps that incident occurred at Facility 3, and they had a low risk. OSHA is going to be questioning you, why do you have a low risk at this facility where everywhere else is a high risk? They're also going to look at what sort of safeguarding did you put in. And once again, they're going to see massive differences between the three facilities. And if your incident occurred at the facility with the fewest safeguards, it's going to look like you didn't care at that facility. So they're going to recommend that you should have put in a lot more based on what your other facilities are doing. Ultimately, this could lead to fines from OSHA just due to these inconsistencies. I mean, on top of those fines, though, there's what I touched on earlier, that if you have inconsistent safety systems across your different facilities, you're going to get inconsistent safety culture, especially if people are moving between the different facilities and seeing that things are different depending on where they go. On top of that, if you are cross-training operations or engineering, it becomes very difficult to do if all of your designs are different. Ultimately, what I think is perhaps the bigger risk here is if you have different levels of safety, you might see people within your organization looking elsewhere and seeing that they have more or less than somewhere else and changing, bypassing, or removing safety equipment based on what they find, which can be a very big problem, especially if OSHA shows up. So ultimately, to summarize all of this, inconsistent PHAs are going to cost you money, they're going to reduce operability, and they're going to negatively impact safety culture, all things you don't want. So that's a bit of a how did they creep in, why did those inconsistencies come up is what we're going to be talking about next. What are the causes of these inconsistencies, at least as RT saw them? And I'm going to talk about three particular things. The first is easy access to process safety information, the personnel experience for likelihood and severity, and ultimately insufficient information for the team to determine an appropriate risk ranking when it comes time to do so. So let's talk about the first, process safety information. OSHA requires a company to compile this process safety information and provide it to personnel and to the PHA team. Now, they give some guidance about what sort of information you need to include in your process safety information. Just a couple of the top ones here are PNIDs, process chemistry, equipment information, technology, and a whole list of other information. The problem here is that often that information is the same across different sources of process safety information, and sometimes those don't agree with each other. Maybe it's as small of a difference as they don't even agree on what the title of the piece of equipment is. Sometimes it can be as serious as the MAWP is different between the different sources of information. So when the PHA team comes across something like this, it is going to change how they risk rank it. First of all, depending on which source of information they use. If Team 1 uses the PNID and Team 2 uses the nameplate for an overpressure scenario, they're going to come up with very different results depending on what the overpressure is. On top of that, if we see inconsistencies in the data, there's a lot less trust in that information. So if I look and see the PNID and nameplate are different, which one do I use? What happens if I use the wrong one? So there's a lot of real impacts if this information doesn't line up. And often what you end up relying on is team experience based on what they've seen or know about this equipment. Sometimes it'll just take a lot longer to do your PHA because you need to look up all of this information. So speaking of team experience, OSHA also touches on what sort of experience do you need in your PHA. And they say you need to have experience in engineering, process operations, and someone who knows the specific PHA methodology being used. That'd be the facilitator. But most of what we document in a PHA comes from the engineering and operations side. And OSHA doesn't define exactly how many years is required in here. That's usually up to the company's procedures or standards to define. But really, no matter how much experience you have in the room, you're not going to have seen everything that can happen. And that comes down to the likelihoods that we're typically talking about in a PHA. We're talking about everything from scenarios that might occur once every year to 1 in 10,000 per year, so extremely rare events. So even if we have a team with lots of experience, there's going to be a lot of events that they will not have seen. To put this on the risk matrix, we have our typical 40-year career fits into the once per year to once in 100 per year of the right-hand two columns. However, for the most part, scenarios that we're looking at, our target frequencies for them are on the left side, between once in 100 per year and once in 10,000 per year. So we really have a discrepancy here between what people will likely have seen in their career and what sort of events we're looking at. Now, I'm not saying in any way that if you have a 40-year career, you're only going to see the things that are 1 in 40. What you're going to see is a variety of the events that can happen on the left-hand side, but not all of them. And to get that kind of experience, you need a much larger team, and eventually it just becomes unwieldy, and your PHA is not going to happen. So what you're going to see, at least in my opinion, this is what I've noticed, is that if you have a team that has not seen the particular event or heard of that particular event occurring, they're going to risk rank it a lot lower, whereas a team that has seen the event is going to risk rank it higher, and possibly higher than is actually realistic. And this is sort of what we saw at RT Industries here. We had one team that had never seen that event and 2 teams that had, and they risk ranked very differently in terms of on the risk matrix, with the top 2 teams being in the upper half. On top of that, even if you have experienced one of these rare events, you may see different severities. What I have on screen here are two very similar events. On the left is West Vancouver. It happened in 2014. An atmospheric tank filled with hydrocarbon overflowed into a dike, and the only impact was a relatively minor environmental issue. On the right, we have the 2009 Caribbean petroleum explosion, where a atmospheric hydrocarbon tank was overfilled, filled up the dike, and then ignited and caused tens of millions of dollars of damage. Luckily, no one was killed in that, but it very easily could have been. So what we're going to have is some of the teams will have experienced just one of these events, and they're going to risk rank depending on what they experience in that particular event, even if it's not necessarily the worst consequence, which is what we're looking for in the PHA. So ultimately, with inaccurate information and differing experience, our PHAs are going to be inconsistent. And that's what I think the root cause of almost all of these inconsistencies that I see come down to inaccurate information and differing experience. So now we know why they occur and what sort of impacts we're going to see. Let's look at some things that industry is doing right now to address these concerns. So not everyone is doing these. These are not necessarily best practices, but rather what some companies are doing to address the concerns, and they're what would have helped a company like RT. The first thing we're going to talk about is process safety information databases that have the right information and can be verified. We're also going to talk about release rate guidance to help people come up with a severity. Lastly, we're going to talk about PHA consequence guidance tables, which help you out in determining the severity along with the safeguards that are available and the IPLs that can be used. So let's talk about the process safety information. So earlier in this presentation, I showed an example of 3 different sources of PSI that are all different. For the most part, a lot of this PSI today is in paper, it's in folders, maybe you have some scanned versions of it, but ultimately it's not easily compared. What I like seeing is taking this information that's available from all these different sources and putting it in one place that makes it a lot easier to access, makes it so you're able to compare it. One such example of a database is ARTS, and what it can do is take your multiple sources of information and actually compare them on the fly so you can see, does this match up with the other information that I have from the different sources? I think for the majority of your process safety information, it's going to line up, maybe 80 or 90%. What this allows you to do is identify that 10 to 20% that is an issue, and ahead of the PHA, you can actually go in and focus on those areas and basically get the right information to the PHA team, which they're going to need to do the PHA. And what that gives is it gives trust in your PSI, and it makes sure that all groups are working off of the same information, which is pretty much invaluable. On top of that, a system like ARTS allows you to look up that information on the fly. I mentioned most of it right now is in paper, and it can take quite a lot of time to look it up. So if you have a piece of equipment, you can simply type it into your equipment database, see that information, and right there it'll show you where it's getting the information from and maybe where there's a discrepancy. And if it does show you a discrepancy, you can ahead of time check, this is the one we want to use. It is the most trustworthy one. So now we have easy access to the information, and we know that it's the correct information when we're in the PHA. Now, there are some potential pitfalls or issues with something like this. The first thing is you need to make sure that the information is up to date. So confirming the database, getting that information in there ahead of time is critical. And running that discrepancy report where you can see where the data doesn't match up and fix it needs to be done before the PHA. It doesn't work well to be an activity within the PHA itself. You're basically just going to slow yourself down there. The other thing is really the data source availability. Obviously, to load it into something like ARTS or similar, you're going to need to have that data available in some way. But based on OSHA's requirements, you should have it somewhere. It's just a matter of really finding where is it, how do we get it in there, and after that, after it's done once, you're pretty much set. You don't need to worry about it again in the future. So to summarize this particular solution, you need to provide the PHA team with correct, accurate, and consistent PSI to ensure that you get consistency in your PHAs. If everyone's working on the same information, that's like the foundation to consistency in the PHA results. The next issue I'm going to talk about is determining the severity of the consequence. So we saw this in RT right at the beginning. Two of the teams said that there would be a permanent disability, one said at first aid. Now, to try to come up with, I guess, a summary of these consequences, I looked across a few hundred higher severe scenarios risk ranked in multiple PHAs, different facilities, different types of units. What I found is the vast majority, 83% of them, fall into two different groups: overpressure of vessels, equipment, and piping, and seal failures of pumps. These are almost fit perfectly within your 80-20 rule of the number of scenarios you're going to see. So if we can address these two scenarios, we can address 83% of the high severity consequences we're going to see in a PHA, and we can get those consistent. It also turns out these are, to a certain extent, the easiest to quantify to the point of a PHA. First, let's talk about seal failure. What we want to know is if you have a seal failure, how much is actually going to leak out? And for this, there's a recommended practice from API 682, which says it's based on the shaft size and the seal size. So based on that recommended practice, you can create a table like this that says if you have a pump with this shaft size, you can expect to release equivalent to a hole this size, for example, 1/8 of an inch. So this would be the area across the hole. If you just punched a hole in the piping, it would be equivalent to a seal failure with a shaft that size. Now, you can also do the same thing, it turns out, with overpressure scenarios. So that's great. These 83% group together in the solutions as well. Now, it's a little bit less exact than RP 682, but this is 581 talks about, depending on how much you go over the design or the MAWP of a vessel or piping, what is the most likely consequences? Now, they talk in terms of flange failure or multiple flange failures or vessel rupture. What I like seeing done is just convert that to what's the equivalent hole size. If we have a single flange failing, it's somewhere around equivalent to a 1/8 inch hole. 2 or 3 flanges would be 1/4 inch. More than that would be 1/2 inch. And obviously, if you severely overpressure, it's going to be quite severe. You can just look at how much is going to be released based on the entire vessel. So now what we have is a way to relate these two, and the hole size allows you to relate to quantity released. So the challenge here is really, how do we get that information? And for that, I'm going to quickly push back to something, to your PSI database, where you can just look up that information as you're going. It'll provide you with things like the shaft size or MAWP. Really handy. Once we have the hole size, we also know the process pressure, and we can use the standard orifice equation to determine what sort of release rate we're going to have. And this is ultimately an estimation, but this equation is well known and quite easy to use when it comes to release rates. Of course, we're not going to ask our PHA team to go through this calculation every time. Ultimately, this is a qualitative, not quantitative assessment. But what we can do is we can use this equation to create some guidance for the team. What I've done here is I've taken that equation and applied it to the different hole sizes and source pressure to come up with how much is going to be released if we have a hole this size. So the way this works is you look at your source pressure. In RT's example, we were looking at 300 PSI. You then look at the hole size. So for the pump, it was a 3-inch shaft size, so that's a 1/2-inch hole. And where those two lines intersect gives you on the left side the quantity released in 10 minutes or whatever period you want. In this case, it says 6,000 pounds of liquid hydrocarbon, in this case, gasoline. So now we've given the team an idea of how much. So is it a really small leak or a big leak? From there, we need to relate that to a severity. And that's relatively easily done. A lot of risk matrices may already have a severity based on the amount released. If not, there's information available based on past incidents or things that have happened in industry that can tell you if you have, say, 6,000 pounds like we just had released, you're going to have most likely a lost time injury. So now we can use the shaft size of the pump or the amount that we overpressure to come up with the lost time injury. Personally, I think that this is one extra step that you need to do and would recommend one further, where we actually put the severities right on that chart. So it's one thing to look up once you know the hole size and the source pressure, and you can see we get the same result. We have a severity 3. Important to note here, these charts are dependent on the material coming out, the density, and obviously the severity is dependent on what's actually being released. You can create these for all of your different products. It would be a lot of work. So what I've seen done that I think is quite good is one chart for liquid, one for gas, and then add variables to adjust the severity up or down by 1 or 2 levels depending, based on what's being released. So for example, LPG is going to be much more serious than gasoline, so we would take this severity 3, bump it up by 1 level to a severity 4. Whereas something that's quite a lot heavier and not expected to ignite, we could probably drop the severity down by 1. So we give these charts and then we give guidance on how to apply that to different materials within our process. Now, there are a few pitfalls to something like this. First of all, occupancy is incredibly important here. If a release happens right next to the control room, it's going to be a lot worse than if the release happens out in the tank farm. And you can address that by changing the severity or having different charts based on occupancy. Personally, I'm a fan of sort of using the local rule here and changing the likelihood based on how likely is it that someone's going to be in the area and modify it there. Also important here is company risk tolerance. When I show those charts and put in the release rates and what is most likely to happen, that is company specific. So you can't just take a different organization's chart and apply it at yours. You're going to need to calibrate that to match your risk matrix and your risk tolerance. And I guess the last pitfall here is if the team has the wrong information, it's easy to come up with the wrong conclusions from charts like this. They also need to very much trust the information. If it seems way out there, it's going to be harder to convince the team to use these values as their severity. So make sure your equipment information is correct with something like a PSI database, and give the team what they need, the foundation, to calculate the release rates. Ultimately, using the release rate charts, we can give teams the guidance they need to pick severities that are realistic and consistent across all of your units and facilities. And I think that that's important. The last topic we're going to be talking about here in terms of solutions is PHA guidance tables. And this is a good way to address the remaining 17% of the high severity scenarios, the other 83 being overpressure or seal failure. And the concept here is that many organizations have similar units across their different facilities. All organizations, at least, have similar equipment throughout all of their different facilities. And perhaps most importantly, industry databases of previous incidents are available and can help you relate the short operating time you have versus the large operating time industry as a whole have. And we can combine these to create tables to help our PHA team come to realistic consequences. And this is a very simplified version of it, but this example here is for something like sour gas treating. Every sour gas treatment plant in the world has concerns around what happens when you lose your amine circulation. What happens if you have a leak, the sour amine? And what we do is we give guidance here. What's the most likely consequence if we have that? So lots of amine circulation is going to create off-spec product, potential for sampling hazards. And the worst that's going to be is a medical aid injury. So what we're doing here is giving a bit of guidance to the team based on what we see in industry. Here's what we think the most likely severity will be. Important thing to remember here is all facilities are slightly different, so that severity can move up or down depending on the design. That's okay. That's something that the team needs to understand is allowed. Secondly, we can actually do that for particular pieces of equipment. For example, the gasoline pump we were talking about earlier. Lock, suction, or deadheading, we can use the release rate tables. But what about something like if the pump stops inadvertently? Now here, something like that is going to depend on the service of the pump, but we can give some guidelines. What are things to look out for? If gravity transfer can occur, consider high level and look at a lost time injury. This is just a small sampling. A refinery would have a much larger chart than this for their various units and pieces of equipment. The next thing we want to do is come up with what are acceptable safeguards or IPLs. And we can just tack that onto here, both the equipment tables and the unit tables. So in this example here, for the loss of suction or deadheading, dual seals is considered a good safeguard and a possible IPL, whereas low or high pressure alarm is acceptable as an IPL if the pump is less than 100 horsepower. So what we're giving is we're giving the teams the information to say, here's the IPLs you should use. If this was RT, they would have had that the pump was less than 100 horsepower and they could use a high discharge pressure alarm as an IPL. There are some pitfalls to something like this. The number one thing you need to look out for is these are not intended to be pre-completed PHAs. The team and everyone involved needs to understand they're for reference to help understand what industry generally sees. The plant is different. The equipment is going to be different across the facility. We can't just build one of these for everyone. On that note, the guidance tables are no substitute for experience. You still need to meet your experience requirements that OSHA requires, your company requires, and the experience that you need to see where these tables don't apply in your facility. Also need to be careful to ensure that you don't allow stagnation in these tables. Things change all the time, company risk tolerance, designs, industry events. Keep these things updated so people trust them within the PHA and they know they can depend on them to help out. Ultimately, what we want to give is we want to give the PHA teams precompiled industry event data to help guide consistency throughout their PHAs. So I've talked about 3 major solutions here: PSI databases with the right information, release rate guidance, and PHA consequence guidance tables, which include safeguards and IPLs. All 3 of these improve consistency in your PHAs. Ultimately, what I'm saying here is you need to provide good foundational information and guides to help the PHA team come to consistent conclusions. So they have the same information, they come to the same conclusions. To wrap up, inconsistencies are going to increase your cost, decrease operability, and reduce your safety culture. And they occur because PHA teams are going to vary and have different experiences, and they may have different information. We reduce inconsistencies by giving guidance to the PHA team to improve accuracy and precision. And ultimately, I did find someone who was saying the same thing I was. Francis Bacon says, to look to make your course regular, that men may know beforehand what they may expect. So thank you. I'm going to turn this over for questions.
Okay, thank you, Patrick. We have a lot of questions, so let's get started. Can you talk about what your thoughts are on the team experience around these inconsistencies? And I think there was a very related question, so I'll read that as well. With regards to the 3 teams conducting PHAs on the event, are they 3 separate teams within the same facility? And if so, is it common and recommended to have multiple teams analyze an event this way?
Okay, well, in the example that I used here, it was actually supposed to be 3 different facilities. Normally, you would only have 1 team analyzing a particular area. However, when you revalidate it every 5 years, it is pretty good to have someone, to have new blood in there, I guess, to get new ideas. So generally, I'd say no, you're sticking to 1 team per facility. But generally, they will vary across geographies. And when it comes to team experience, again, I can't really give guidance in exactly what's required. OSHA requires the engineering and operations experience. They don't define what that is, but it should be enough that they know how the process works and how it reacts to changes and faults that occur within it.
Okay, thank you. Wouldn't you further evaluate the causes of overpressure and address that after the PHA?
Yes, depending on what the scenario is. If you have an overpressure, at least I think that the question here is around, do you look at dispersion? Do you look at how often people are in the area? Do you do essentially a QRA? And some organizations do a quantitative risk assessment further after the PHA. I wouldn't exactly say that is common in industry right now. You may do dispersion modeling, and that's a good thing to have. What these guidance charts are giving you is a basis of what sort of severity can you look at. If you can protect against that severity, which is, I guess, in many ways the worst case, you should be good. And if you can't, that's where you probably want to go on to something a little bit more rigorous and analyze that further.
Okay, thank you. Can you please suggest a good resource for PHA guidance tables and safeguards IPL?
There is not a industry database out there that says if you have this type of unit, you're going to have this type of concern. This is usually built within companies based on their experience and what they see happening around industry. So the data source for that is going to be internal events that have occurred, as well as industry events that have resulted, that have been reported on. So I think it would be great if something was organized to look at these different facilities across companies and compile this a little bit better. But right now, there's not a lot available. You can look at AFPM for some incidents, but unfortunately, there's no industry-accepted compiled table like I showed in here.
Okay, thank you. Can you give any examples of sources for industry incident databases?
Okay, that, as I was mentioning there, AFPM does provide that. I believe that the Center for Chemical Process Safety also has a similar database, and ultimately you can look at the Chemical Safety Board is an excellent resource to look at the really high severity ones that happen quite rarely. Actually, I can't speak highly enough of their investigations and videos that are incredibly useful in seeing how these events occur and what you can do to prevent them in your facilities.
Okay, thank you. One attendee was curious he had a few questions about some of the acronyms, the ARTS, ARTS, MDMT, and PSI.
Okay. So ARTS is just it's a software database that holds your process safety information, which is your PSI. It's just shorthand that is used based on the guidance from OSHA in terms of process safety information. So ARTS is actually a proprietary software. And the last question was MDMT, which is your minimum material temperature. So if you're looking at concerns around low temperature, you need to see that when it comes to the PHA, so exceeding the design temperature on the lower end.
And PSI was his other question.
That was process safety information.
Oh, okay, you got that. Thank you. Let's see. I'm starting PHAs with my facility. I have considerable experience, but my teams will be rather inexperienced to the PHA process and safety reviews in general. What are some best practices you suggest?
Well, the biggest thing I've seen with PHAs and inexperienced teams is it takes quite a while to get into the actual process of doing the PHA. They may have, it wasn't exactly clear there whether they have operational experience or engineering experience. I'm going to a certain extent, assume that they do because that's required. Now, when it comes to actually doing the PHA, I actually have a lot of experience in that area, and one of the things you need to do is start with some training, even if it takes hours. Sometimes it can be a full day training course on how the PHA actually works. It's not with the intent of allowing the participants to facilitate it, but rather know what the expectations are. So when we talk in a PHA, perhaps the hardest thing to do is come up with the consequence without safeguards. That is a constant struggle, and understanding why you need to do that, what the regulations say about doing that, and how the industry works in general in terms of consequence severity is great. And if you can spend, I've seen it take an hour to 2 hours to explain why that's important and what you need to do, and that gives the basis for going forward, and you'll have a lot less fighting once you actually get into the session. On top of that is knowing safeguards, especially if you're doing LOPAs, so IPLs. The team really needs to be able to understand what is a safeguard that's going to adequately work, and particularly in the IPLs, it can be rather frustrating to a team that doesn't know why you want IPLs. It can be quite frustrating to look for independence when really they're usually used to seeing alarms or trips that just work. So one of the things I like to do is look at the CSB incidents, for example, and you know, their Texas City video is a great example of why you want to do a LOPA and why you want independence between the safeguards, because in their example they had tons of safeguards, but but they weren't necessarily independent and they weren't reliable, and so we saw the eventual event that happened there. So I highly recommend doing some sort of training ahead of time, especially for a long PHA. If you're going to be sitting in a room for 5 weeks, it doesn't hurt to take half a day for training.
Okay, thank you. For a facility with batch processes where certain processes are covered under different regulations like PSM, is it acceptable to have different formats for PHA's risk assessments, or should the facility have one particular format?
I think it's all right to have multiple types between risk assessments and PHAs. You don't want to do double work, but there's definitely a lot of organizations out there that split out risk or hazard assessments and PHAs. So I don't think there's anything wrong with that. What you probably want is for your different facilities within the company doing hazard or risk assessments, doing the same type of risk assessment on the same process or the same hazards. That's pretty key, especially if OSHA shows up and they were expecting a PHA and you just did a quick hazard review. That's going to cause some problems. So you want to give some guidance there. Look to define your company standards and procedures to help define that.
Okay, let's try and sneak one more in. I thought that when a PHA team looks at likelihood, it should be mitigated, no layers of protection. Did I misunderstand?
Well, that's when you look at severity, generally that should be without your safeguards and completely unmitigated. And that's based on the OSHA requirement that we look at the failure of safeguards and what occurs. However, there isn't actually anything that says you need to look at how likely the events are to occur if you don't have any safeguards, just the consequences thereof. So it can be really good to have the risk ranking before safeguards and then add in a risk ranking after safeguards. But it's not that unusual to have a company skip the first step and just look at what is the severity without safeguards and the likelihood with safeguards, and that gives us our risk ranking.
Okay, thanks very much. I'm sorry, but that's all the time we have for questions. So if anyone still has a question that was not answered today, please send it to producer@aiche.org, and I will forward it to Patrick. So now, on behalf of the American Institute of Chemical Engineers and everyone who attended today, I'd like to thank Patrick Fisher for this very informative talk. Thanks also to our participants for your cooperation and thoughtful questions. Please visit aiche.org to replay this webinar or to view and sign up for our many others. Goodbye, and we hope to see you again in a webinar soon.
Thank you, Pam.